Hello, I am Luis Contreras, and I will present our latest work on service robots at the Advanced Intelligence and Robotics Research Center in the Tamagawa University. The application of robots in many fields has been extended rapidly in recent years. From industrial robots to space explorers, now we can find them performing home services. A service robot is a robot that can assist humans to perform common daily tasks in shared environments, such as houses, offices, or hospitals. To achieve this, a service robot must be capable of understanding spoken and visual commands in natural ways from humans, navigate in known and unknown environments while avoiding static and dynamic obstacles, recognize and manipulate objects, detect and identify people, among several other tasks that a person may request. The presence of service robots in domestic environments is increasing recently, and, in consequence, the familiarity of users and the difficulty of the tasks that they may request. Therefore, standardization on full task performance, in contrast to individual skills evaluation, is necessary to compare different software and hardware implementations. Furthermore, complex scenarios in natural places are preferable over controlled laboratory spaces. Although several applications have been developed, they mostly are skill-specific and highly depend on the experimental setup. It's in this context that we propose the Tidy-Up task as presented at the World Robot Summit Partner Robot Challenge as a benchmark for general-purpose service robots performance assessment, where several skills can objectively be evaluated in human-like scenarios to mark trends and challenges in this area. To help a service robot to solve this task, we are applying unsupervised learning on some basic robot skills. First, we present a very economical framework for multi-view object recognition based on hidden Markov models that can be trained using a really low number of images, using a flat computer and in short times. The resulting model is able to recognize the objects and infer the camera trajectory from a new sequence of query images. We evaluate our system for object recognition with single shot and multi-view shots in the Columbia Object Image Library, a dataset of color images of 100 objects taken from different points of view. The experiments include the variations in the test images for validating the robustness of the method in the presence of Gaussian white noise and object rotation in the yaw angle. In the tables, you can see the results for different vector quantizer sizes using forward and backward sequences. The first column refers to a single shot inference, while the second one shows an inference using 4 shots without noise. Similarly, the third and fourth columns include Gaussian noise in the query images. It can be noticed the improvement in classification using multiple shots. Finally, the confusion matrix using 4 shots and 512 centroids is a diagonal matrix, showing a good performance in the recognition task. Then we present a task-based map compression techniques useful for path planning and navigation in indoor environments for service robots, where, from a point cloud of 3D map features, we calculate a number of clusters based on their spatial position and generate a sparse 3D representation of the environment. Moreover, we propose several metrics to assess the quality and performance of a map representation, and we tested our proposal using a series of point cloud benchmark and clustering techniques, where our method has a comparable performance using a fraction of the memory footprint than the baselines. In the experiments, we created an octomap-based occupancy grid and a sparse map from the same point clouds. We sampled 1,000 start and goal points from these maps and requested a plan between these points. Our first matrix, the path length L, is the sum of Euclidean distances between all consecutive points in a path P. We had a similar length on average, but our method computed them faster. This is associated to the smaller graph size we generate. Sparse maps have less than a couple of hundred nodes, while occupancy grid can have over 1,000 nodes to plan. Then we have the angular tortuosity T, where U and V are line segments defined by 3 consecutive points in the path. Here, we observe that our method generates paths with smaller tortuosity. Next, the translational dispersion D is the standard deviation of the points P with respect to the path centroid P hat. While sparse map generate paths with small tortuosity, they presented a higher dispersion. In other words, our method generates paths with little rotational movements, but they are more jagged than the paths from the dense planar. Finally, we have released our system as a ROS-based open source library. To generalize the application of service robots, we are working on complex action planning by combining general-purpose service robots models based on expert systems with the standard and data-driven skill models. And then we evaluate them in real scenarios explicitly designed to test such systems, like robot competitions. Our current work focuses on action planning by using semantic reasoning to generate a global plan from a given command, spoken or in a command line, while we integrate standard and data-driven skills models with human intention detection and active reasoning to generate local plans for low-level behaviors. Thank you for your attention.